Welcome to the course on power quality. We will cover 3-phase AC/DC improved power quality converters. Coming with the outline, we will like to introduce, then we will talk about classification of 3-phase improved power quality converters. Then we will talk about principal operation and control of 3-phase improved power quality converter, analysis design of improved power quality converter. We will have some numerical examples and summarize, and we will have given the list of references. Now, coming to the objective, first we will like to discuss requirement and the application of these improved power quality converters, and we will talk about configuration of the 3-phase improved power quality converter and followed by control and analysis design of the 3-phase improved power quality converter. So, coming to the introduction part of them, the parallel to the development of single phase improved power quality converter, numerous concepts of for 3-phase improved power quality converter have been proposed and analyzed over the last 2 decades, and 3-phase improved power quality converter offer excellent performance characteristic both from input and output perspective at a high power level, and such converters are extensively utilized in various applications from 3 kilowatt to hundreds of kilowatt power rating. And similar to single phase improved power converter, the essential performance characteristic of 3-phase improved power quality converters are also summarized as with the supply input current, sinusoidal supply input current according to the various regulation regarding the mains behavior of 3-phase system with EN 61,000 and typically for less than 16 ampere, 61,003 for more than 16 ampere, and a high power factor operation also AC mains, regulated output voltage depending upon the required level of output DC voltage at system with boost, buck and buck boost type characteristic, and of course, with the EMI compliance, electromagnetic interference compliance, and mastering of AC mains failure, that is for interruption of one mains phase continued operation at reduced power or unchanged sinusoidal current shapes should be possible. So, these are typical applications of these converters like maybe solar grid interface system, solar energy conversion system, wind energy conversion system, where these converters are taking really a big application. So, we will like to have even later the case studies of them, and then the other application like AC microgrid, where you are connecting, because you are including the DC sources also similar to like a fuel cell, then solar PV generation, variable speed wind power generation, and including the battery energy storage for making the microgrid. It means you are using several such converters which really does not tax by power quality problems on the AC side. Because you have a AC bus, so AC bus will not be affected by power quality problem either by these renewable power generation or conventional generation of DC set as well as the connected load on this AC bus. Then other, of course, they are also important for DC microgrid also, where the you are connecting this with the AC grid for transferring the power. So, power quality problems will not be either on DC side as well as AC side. Then coming to applications like HVDC system, HVDC system is quite old applications even for since 1954. So, earlier we were using the thyristor converter typically with the passive filters, but nowadays we start using voltage source converters with the benefit of that you are able to eliminate, there is no need of reactive power, virtually you are able to generate the reactive power by voltage source converter required on AC side during contingencies or otherwise, and moreover it does not draw harmonics and there is no need of bulky passive filters. You require very small ripple filter similar to what we discussed already, voltage source converter. So, new breed of HVDC system we using the different names, we call it HVDC light or we call it HVDC plus. So, their concept by the industry has put by these converters which have a good power quality without filters with the bidirectional power flow in HVDC system. They are developed for many applications for like a wind farm and a solar farm also. And other major applications is coming electric vehicle charging station, which even now for these converters, so that the you are not having a power quality problem on the grid, because you are drawing the power from the grid and you make sure that neither the reactive power burden is on the supply on AC mains as well as harmonics are also not injected by this electric vehicle charging stations or chargers Well, coming to another application to traction system, traction system also now we start putting like a typically traction not only include like electric traction, but it also include the metro. So, we start putting now typically voltage source converters on the grid side typically, so that neither the harmonics nor the reactive power burden is put on the grid, but actually you should be able to support the reactive power if required. And then cold storage plant, you are using large number of variable speed drive as well as DC set into typically in cold storage as well as energy storage. So that you should not have on AC grid the power quality problem. So, you are selecting the right converter, improve power quality converter for these applications like. So, high power electric drive system for various applications where you use the medium voltage drive with the power quality improvement like in cement industry, mining and minerals industry, metal industry, marine and chemical industry, oil gas industry, and of course, water industry and many more applications. Now, coming to the classification these of 3-phase improved power quality converters, we classified into them into like a based on power flow like a unidirectional power flow and bidirectional power flow. Unidirectional power flow, the example I can talk about typically like a medium voltage drive for large air conditioning system or refrigeration system, where the power flows into the one direction, but typical example may be of bidirectional power flow of these converters are the typically like a traction, the active load where we are connecting them, and of course, we classify unidirectional further into like a category of boost, where you are having a boost operation, buck boost operation, multi-level operation, as well as we have multiples converters also, that is also coming as a big way. We will like to discuss in a typically in separate lecture like. Similarly, for bidirectional also we have a boost, buck boost and multi-level and multiples like. So, you have a typically these 10 category of these improved power quality converter in 3-phase connected supply system. So, coming to like a typically 3-phase unidirectional boost converter, improved power quality converter. This is the first that we want unidirectional in the sense that we have here typically 3-phase diode rectifier with the boost converter. Of course, it cannot give a too good power quality on the supply side, and that is the reason we connect typically this you can call it T filters on input, which are able to provide the harmonic reduction into this, and you get almost like a closer to unity power factor on the supply system, which is normally used in lower rating like also. Then we have a typically another converter 3-phase 2 switch unidirectional boost converter using zigzag injection transformer. This is also known as Minnesota rectifier. This was virtually invented in Minnesota University, and that is the name they put like a Minnesota rectifier. So, you can see it is with the you can call it like injection transformer here, and you have a 2 boost converter to regulate the output voltage. This is you can have a harmonics quite here of course, and unity power factor on this side, and of course, if load needs only DC you can have this. It provides the boosting features because you are having a boost converter here. Apart from that, it has a very interesting feature that if you have require a load like 2 equal voltage across the load DC load like similar to like a switch reluctance motor drive midpoint converter, you can provide this also from this converter like. Then coming to like a Vienna converter, this is again invented by Professor Kohler, who has been in the Vienna University in the Vienna, capital of Austria. So, he put the name on the city, so called Vienna rectifier, and this is with the 3 switch PFC converter. It also boost converter and give a almost good power quality on the supply side. This converter has become very popular, many versions are there, we will discuss in detail, and you can use of course on load side. But if you want 2 equal voltage across for load, which I will already mention that similar to like a midpoint converter or switch reluctance motor drive, you can use this converter. Of course, it is very much used in telecommunication industries like and also. So, another your unidirectional is that you can take a Scott connection of 3-phase supply, and then you can have a 2 converter PFC with the equal power sharing to get output voltage. So, you have a, of course, the isolation, and if you have a balanced load on this Scott connection, you have a balanced current in the supply system, as well as you get of course, the power factor correction because of this PFC boost converter operating in this case like. So, you are able to regulate the output voltage with the good quality TAT, but only the drawback is that you are using power frequency Scott connected transformer, which are not in other circuit like, but of course, you are getting isolation. So, it depends on your application requirement if you are using this like. Now, coming to 3-phase bidirectional boost improved power quality converter. This is 3-phase bidirectional boost converter, one leg is replaced by midpoint capacitor. So, because of whole current of this phase move through this capacitor, value of capacitor is very large. So, this is not considered quite good, and voltage output have to be very high, and of course, this is the very well justified converter which can have a bidirectional power flow, and this is used of course with the bidirectional power flow in the sense I can say normally used for solar grid interface I mean like, and sometimes we have energy storage like a battery in solar grid interface on the DC side. So, in the night we do not have a solar, you can charge the battery also from this at unity power factor, and you can put the solar power injection to the grid on the unity power factor. So, such converters are also now becoming quite popular for renewable energy interface with the energy storage on the DC link itself. So, we will like to discuss that case study separately like also. Then coming to of course, the fourth leg here with the midpoint, to improve the performance of this. Similarly, fourth leg is taken here for the sometime for neutral current compensation kind of things. We will discuss little later. So, now coming to typically boost type power factor correction rectifier Vienna converter, or it is also called delta switch rectifier, and this is another version of typically of Vienna rectifier, where the bidirectional switches are connected here, and by modulating this you can make the 3 current sinusoidal. Of course, in this case you are able to reduce the number of the devices, and you are able to get like a supply current in phase with the supply voltage with properly, and of course, with proper design you are able to get low input inductance requirement of these with the, if you operate reasonable switching frequency, low switching losses and low MI and higher circuit losses. So, these have become very popular for telecommunication industries like because you have to charge the battery virtually from the your either from DG set or from the grid, but maintaining the good power quality means good power factor and reduce harmonics and no reactive power burden on the supply system. And these are the typical of course, the waveform that how you are able to get supply voltage and supply current with the different kind of switching of the devices bidirectional switches and how the different voltage, and you are able to even use the typically sometimes phase factor modulation for pendulum switching. Of course, these are the different modes of operation. Like here you can have a typically 8 modes of operation of these converters for the purpose of switching, how you really are able to get boost operation as well as maintain the power quality on the supply side like. And this is typically the another version of this we call it delta switch converter virtually for unidirectional power flow, and where this switch are not connected virtually, they are connected in delta manner, they are not connected star with the midpoint. So, the benefit that you do not need the 2 capacitor here on the DC side, and it is able to control the, you can call it output voltage regulator, as well as you are able to get sinusoidal current on input side like. And you can see the 3 phase supply voltage with 3 phase typically the voltage, and you have a 3 phase supply current from this converter. This is typically for 5 kilowatt converter. How you look into the assembly, these are very popular with the high power density you can think about. For use for again for telecommunication industry and many industry for with power factor correction on the supply side like, and how the pendulum switching pulses are generated for those bidirectional switches like. So, now coming to 3 phase unidirectional buck converter, and this is simple buck converter that you have a buck converter after diode rectifier, and it is a replacement of, you can call it typically like semi converter of thyristor converter type, and you have a like of course, single switch cannot have a good power quality on input side, but you choose the LC filter to save the current of course, on input side of this converter or to get reasonably good power quality. But of course, we use the typically we call it this is 2 switch derived converter similar to like what we talk about another converter with the ripple injection similar to Minnesota rectifier, but this is for buck operation, 2 converter operating in buck mode for regulating output inductor, and this ripple injection circuit you can of course use the zigzag, or you can use this star with the closed path of the for ripple injection with the delta circuit. So, this all of course provide the, so you can call it is a complementary of Minnesota rectifier for the buck operation, and you have again the buck converter corresponding to again complementary of your Vienna rectifier for buck operation with the 3 switches and with the MI filter. So, it also give buck operation at the output voltage, and similarly now this is what we call it the typically buck operation of the 3 phase current source converter with the only freewheeling diode at the output with the filter, and you are able to get of course, the well shaping of the current on the input line. So, these are the version of unidirectional buck converter. Now, coming to 3 phase bidirectional buck converter, this is typically you can think about is a we are using the GTO here the switches with the input LC filter, because the reason being these currents are the pendulum current here, because you will be operating this converter in PWM mode, and this is the replacement of thyristor converter. The benefit compared to thyristor converter of this is that there is no reactive burden as well as no harmonics on the supply side, and you are able to get a control voltage at the output. Of course, why you selecting a GTO? GTO have a gate turn of thyristor, have a reverse voltage blocking capability, which this current source converter needs here, and Of course, the limitations of this is the GTO cannot operate high switching frequency, so you cannot have the size of filter lower, but you can use the IGBT with series diode for this converter. So, that allow higher switching frequency and you can reduce the size of this typically of the EMI filter or output inductor also for 3 phase especially. And this is the circuit with the IGBT with series diode. The reason big, this is a current source converter and you have a pendulum current here, and it needs the reverse voltage blocking capability across the switch. That is the reason IGBT or MOSFET, I mean your transistor family does not have reverse voltage blocking capability. That is the reason for reverse voltage you are connecting diode. So, one of the major drawback of this is that the now losses of the two devices are there, not one. I mean like, and you need of course, because it is a pendulum current, you want a here continuous current. So, you need the this capacitor, shunt capacitor, and value of shunt capacitor certainly depends on the value of typically of your switching frequency like. But of course, I mean here the drawback is that this is also mandatory and you need the inductor filter, where the boost converter do not need this inductor filter, only capacitor is enough like or they. So, again this is again the you can say replacement of, you can get a bidirectional voltage at the output, but current will be unidirectional because inductor is there similar to like a thyristor bridge like. But compared to your thyristor converter, bridge converter, the benefit here you do not have a reactive power burden and you do not have a harmonics, that have a harmonics as well as reactive power burden. I mean like also. Now, this is typically again with the fourth leg corresponding to take care of the typically improved characteristic corresponding to the with this fourth leg for corresponding to the neutral leg. Now, coming to like a buck type power factor correction rectifier system with the 6 sets, a switch rectifier, and this is similarly again you can call it derived to similar to complementary of Wiener rectifier for buck operation. So, you have a switches here typically with the capacitor, here also again you have a pendulum current and you have a certainly the output filter inductor for. So, this is the typically you can call it the again the how the converter look like for 5 kilohertz, and you are able to get virtually even buck operation corresponding to 400 volts, otherwise the peak of 400 will be much higher of the line voltage, and these are the supply current which are balanced sinusoidal in the supply side like. And then typically the corresponding to the losses, how losses and efficiency are there. So, you are able to get quite good efficiency of 98.8% in this converter also, and this is typically you can call it like a your extension of your 3 switch buck boost topology. I mean here you can see you are using the buck converter here and this is the boost converter. So, it is a 3 phase buck, so that you get the sinusoidal current on supply side and followed by the boost. So, that you are able to get a operation of buck boost converter in this configuration like. And then the switch rectifier, I mean typically corresponding to here the boost operation, these are the buck operation. So, you are able to get buck boost operation corresponding to this switch converter like, and the control of this converter like. I mean, so it totally depends on the typically on requirement of your application with power control, and you can just clearly see how the typically like a 3 phase voltage and how the typically coming like a 3 phase current, I mean typically on the supply side, and when you extended it how the pulse switching take place in this converter. Now, a comparative evaluation is given here for this Vienna and delta as well as the switch 6S converter, and these are the typically the you can call it performance indices corresponding to your calculation of KVA rating and losses calculation for all components of the transistor, diodes and passive component and the conducted noise corresponding to this, and based on that for Vienna and switch converter it is the your delta switch converter, this is for Vienna rectifier, and this is again for your switch converter, and this is for corresponding to your 6 switch converter, like how they look into the performance corresponding to 10 kilowatt. They are used very extensively for telecommunication power supply, even for 72 kilohertz order of that like, and these typically the current stresses calculation corresponding to this configuration of your Wiener rectifier. So, Wiener rectifier have many configuration, I mean like also. So, that is about delta switch configuration calculation for all components like also stress component. So, they are used very much in telecommunication industry, that is the reason I mean like they are developed with the high power density for 3 phase around 5 to 10 kilowatt power. Now, coming to 3 phase unidirectional bidirectional buck boost converter, this is you can call it the buck operation followed by the boost operation for buck boost unidirectional converter, and then this is again you can call it like a simple current source converter with LC filter, and then you have a typically the CUC converter for SEPIC converter I mean typically SEPIC converters which can give the buck boost operation like also, and this is typically Wiener rectifier 2 where you can think about the buck boost is derived only by one switch, and it is an interesting circuit and you are able to have a current wave shaping and you are able to get this only by one switch with the injection one properly to get the regulated output voltage of buck boost operation with the help of single switch, similar to flyback converter. And this is similar to like after this you have of course the LC filter and you have a typically high frequency Cuck converter at the output, I mean operating with DCM4 typically for power factor correction converter with isolation also. And of course, this is 3 level, I mean you can have a multi level typically created level here also for improving the power quality on the supply side and having a boosting operation with the help of the 3 switch bidirectional switch. So, this is nothing but the bidirectional switch with similar to like what we discussed typically of corresponding to like your Wiener rectifier, but number of the levels are increased in this case. And this is the bidirectional buck boost converter. This is derived from matrix converter, because matrix converter is a very converter which can do all 4 conversion AC to DC, DC to DC and AC to AC, but here it is derived for AC to DC with the bidirectional power flow. I mean like and of course, on input side it work like a control, output side work as a typically because you are connecting inductor. So, you can have a bidirectional power flow and with the buck boost operation for the output voltage like. So, now coming to the numerical examples of them. So, coming to the first numerical example, 3 phase bidirectional boost PFC converter draws 10 kilowatt from 250 volt per phase 50 hertz 3 phase AC means for resistive load, the switching frequency 20 kilohertz and inductor input inductor is 2.5 millihenry. The power factor is corrected close to unity and PWM modulation index is 0.8. Determine the output DC link voltage, value of equivalent resistance of the load and phase shift between fundamental component of PWM, I mean which are derived from this and the supply voltage. So, this is the typical circuit for this converter which can have a bidirectional power flow. So, coming to the calculation part of it, we have a 10 kilowatt 10,000 watt and phase voltage 250 volt with the interfacing inductor 2.5 millihenry. So, we can find out the fundamental you can call it the current considering power factor proper control power factor correction. So, we get current on supply side 13.3 ampere. We can find out the reactance of the input inductor for corresponding to fundamental frequency. So, it comes after from 2.5 millihenry putting the value, it comes like a typically of your 0.785 ohm and the voltage drop across this for given current. I mean you can have XL into IS1, it comes 10.4 volt and the converter fundamental voltage from typically from the phasor diagram you will get VSC square plus VL1 square. So, you put the value this 10 and 250, you get 250.22, that does not change much of difference in VL1 and typically converter voltage, and you can find out the DC link voltage from the typically for this fundamental converter voltage from this relation, you get 884.6 volt and typically now for from power relation, I mean 3 Vs V converter 1 into sin delta into XS for power flow in equivalent to power system, we get the power angle that called delta or phase shift from this sign relation, putting the value of all of them, it comes 3.05 degree. So, it has a very good stability because this angle is very low. I mean like, and the reason being that you are putting very small reactance here, not very large reactance and quite very low inductance also, and the equivalent resistance is calculated to be DC upon power. So, that comes 78.26 ohm. So, coming to second numerical on a 3 phase voltage source converter feeds a power of 25 kilowatt to 415 volt 9 to line RMS 50 hertz 3 phase AC means from 720 volt DC bus and switching frequency 10 kilohertz and AC inductor is 2.5 millihenry and power factor is corrected close to unity. Determine the PWM modulation index, RMS supply AC current and phase shift between fundamental component and PWM voltage and supply voltage. So, this is the typical circuit of voltage source converter with bidirectional power flow. The input inductor is there and output capacitor, and it can operate, I mean you can call it boost converter like. So, coming to solution, we have a power given 25 kilowatt 25,000 and voltage RMS is 415 volt line and inductance is 2.5 millihenry. So, we can calculate fundamental current drawn from supply at unity power factor. So, putting the value of all, we get this as a 34.78 ampere and the reactance of this which are putting on supply side of 5 millihenry, multiplying the frequency in radian per second, it comes 0.785 ohm, and then the drop in this corresponding to rated current, we put value, it comes 27.3, and converter fundamental voltage will be VSC square, because they are at quadrature this inductor drop for unity power factor. So, it comes 241.15 volt, and from this we can find out from this relation the DC link voltage corresponding to given converter fundamental voltage, and this we can, because DC link voltage is also given, we can find out modulation. So, it is operating 0.947. So, it is operating in linear modulation 1, and from this power flow equation 3 into Vs into fundamental converter voltage sin delta divided by x, we can find out the phase shift between your fundamental converter voltage and supply voltage from this relation. So, it comes 8.29. Still the stability is quite good, but this angle is quite low compared to power system. Now, coming to third numerical problem, a 3-phase 12 pulse bidirectional boost converter IGBT based voltage converter draws 10 kilowatt from 250 volt per phase 50 hertz 3 phase AC means, and sinusoidal wave voltage, and AC inductor is 15 millihenry, and displacement factor is typically close to unity. The VSC is operated in mode to cancel 5th and 7th harmonics in output voltage, determine the phase shift of the fundamental component of voltage source converter, AC voltage and supply voltage, and second fundamental phase current, 11th harmonic current, total harmonics in AC voltage, and TAD of all AC voltage. So, what we are having here typically using 12 pulse converter, and the difference here is that the grid side we are connecting them the transformer in series, and the load side we are connecting them in parallel, because the same DC link voltage we want to apply this. So, we are using 2 voltage source converter. We can of course have a either feed the load here, or we can have a even the solar injection or the bidirectional power flow in this voltage source converter. Now, in this case because it is a 12 pulse converter, we can operate at 180-degree mode of these two converter, so that the utilization of devices is more, and you can call it switching losses are less, which are normally used for a very high power applications like. So, given here you have a like a 10 kilowatt 10,000 watt, and voltage per phase is 254 volt, and your interfacing inductance of this you can call it like a including the input inductor and leakage reactance of transformer, which can be adjusted 15 millihenry. So, we can find out the fundamental current from power and this relation of VI. So, considering power factor unity, it comes 13.123, and the reactance for given 15 millihenry we can find out the reactance of it comes 4.71 ohm, and the inductor drop for fundamental voltage will be your XL into IS1. And now, we can find out fundamental converter voltage by this relation VSC square plus PLE square. For unity power factor, these two voltage will be at quadrature. So, it comes 261.41, and the now phase shift from power flow equation by putting the value voltage and reactance and supply voltage and converter fundamental which we calculated, we can get a phase shift. So, it comes phase shift of 13.677 degree. Now, coming to typically calculating the harmonics, here we will be getting the harmonic, because it is a 12 pulse converter. So, we will get a voltage harmonics fundamental divided by order of harmonics. So, with this relation we will get 11th, 13th, 15th, 23rd, because these are the 12 pulse converter. So, you will have a 12 n plus minus 1 harmonics in the voltage at the input when you are connecting, other will cancel out. So, you will have all voltage harmonics, dominant harmonics up to 49, and then the current harmonics will be corresponding to V1, this is the voltage divided by n XL, XL is fundamental reactance. So, it will become your IN equal to V upon n square into XL, then we can calculate the 11th harmonics. Now, 11th harmonics current will be like a 121 11 square into the fundamental reactance. So, it will be 0.4, and 13th will be this, and you can see the how the harmonics current are automatically further reducing drastically down because of this factor of n square there, like compared to the voltage harmonics. Now, we can calculate the TAD of the voltage. So, we can take all the dominant harmonics to calculate the TAD, and it comes 14.17. In 12 pulse it comes at the order of 14 to 15%. So, it is because we neglect some of the harmonics, it comes quite closer to that value, and the current harmonics like we calculate all dominant harmonics. So, it is only the TAD come 0.0456. So, even for this 12 pulse converter in voltage source converter, you are able to get current TAD only order of 4.456, which is well accepted by many standards. So, it means you can operate the converter in fundamental switching frequency mode and get the TAD less than 5% for 12 pulse converter. and utilization of the converter is full, because you might operate the devices in 180-degree mode of operation. Now, coming to the fourth example, a 3-phase 12 pulse quasi-square bidirectional AC-DC converter, IGBT based voltage source converter coupled with the transformer, having a primary connected to AC means star delta and delta delta with common DC bus, with a fundamental frequency switching and feeding 50 kilowatt from the DC battery of 720 volt to a 254 per phase 50 hertz 3-phase AC main, and fifth harmonics current is to be limited by 20% of the fundamental to each converter and displacement factor corrected to unity. The VSC are operated in a mode to cancel fifth and seventh harmonics in AC mains current. Determine the A transformer turns ratio, B phase shift of the fundamental component of VSC AC voltage and supply voltage, and C the fundamental phase current, and D total harmonic distortion of AC mains current, and then E the value of leakage inductance of the transformer. So, coming to the solution part, we can find out the fundamental current from power and voltage for unity power factor. So, it comes around 65.616 ampere, and the transformer turns ratio for given voltage required 720 volt is the battery, and we have a voltage of fundamental voltage typically of supply 254. So, turns ratio comes 0.274, and the fifth harmonics current to be limited 20%. So, for this the reactance comes 0.2 ohm per unit, and then from this we can find out the base impedance, then we can find out the your reactance, interfacing reactance for 20% of it. So, it comes 0.77, and we can find out fundamental converter voltage from your supply voltage plus this converter, this reactance drop corresponding to fundamental current. So, it comes 259.030 volt, and this is the typical circuit. On this side we connect them series, this side we connect in parallel like. And then the phase value of phase shift we can calculate from this power relation P x upon 3V and converter fundamental voltage. So, phase shift comes like 11.31 by putting the value of all the components, and the fundamental current comes 65.616 we calculate, and TAD of AC current comes 5.3. So, from same relation for 11-12 pulse converter we can find out dominant harmonics, typically 11th harmonics, then 23rd, and typically 35, and 11 13, then 23 25th, and then 35 37, which are 12 n plus minus 1, and adding all dominant harmonics we get the TAD order of 5.36 only in this 12 pulse converter, and the value of interfacing transformer, I mean we calculate from this, it comes 2.46 millihenry, which adjusted the leakage inductance of the transformer like. So, coming to now fifth example, design a 3-phase uniaxial boost PFC AC-DC converter operating at 20 kilohertz using 3 identical single phase PFC AC-DC converter for power rating of 12 kilowatt from 254 volt per phase and 50 hertz AC mains for a battery charging application. The displacement factor is corrected to unity. Determine A output capacitance sufficient to make output voltage of 400 volt with the ripple of 2% and the value of inductor for PFC. So, now coming to the solution, power output is given 12 kilowatt and DC voltage is 400 volt, and V input average will be 146.65 and 50 hertz, and switching frequency taken 20 kilohertz. So, ripple RMS input current will be from power for 3 phase, it will be calculated from. So, it comes 27.28 per phase, and the output current will be PVDC. So, putting the value it comes 30 ampere, and equivalent resistance comes from this power relation 13.33 ohm. And now output capacitor from this typically from duty cycle relation. So, duty cycle comes 0.4817, considering the output DC ripple of 2%, the output capacitor for second typical harmonic comes around 5.97 millifarad, and the value of PFC corresponding to 2% input current ripple, we can find out input current, ripple current, and then from this we calculate the inductance of 6.5 millihenry like. So, coming to 8th example, a 3-phase 6 pulse bidirectional boost AC-DC converter GTO based voltage was connected through a star transformer, feeds a 25 kilowatt from a battery of 760 volt to 254 volt per phase 50 hertz 3-phase AC mains with and sinusoidal wave shape. The fifth harmonics current is to be limited 10% of the fundamental current, and VSC is operated in mode to cancel third harmonic VSC output. So, displacement factor is close to unity. Determine the turns ratio of the transformer, value of phase shift of fundamental and AC fundamental component of VSC AC voltage and supply voltage. See the fundamental phase current and 13th harmonic E TAD in AC voltage and F TAD of AC mains current and G value of inductor. So, coming to numerical part, we have a power here typically of 25 kilowatt and V is equal to and 10% ripple of IS1. Taking a modulation index, we can find out IS1 from this relation. It comes 32.8 ampere, and we can find out typically turns ratio of the transformer. So, it comes typically of 0.4, and we can find out fifth harmonics, which is limited to 10% of fundamental 3.28, and converter voltage from this relation we can find out typically 268.7. Then we can have a even the reactance corresponding to this fifth harmonics, so it 3.28 and inductance of 10 millihenry. So, phase shift for fundamental component, once we put the value in power transfer relation, so it comes 23.578, and fundamental current we already calculated, and harmonic current will be V 1 upon n square A x s. So, we can find out fifth harmonics 3 point, then seventh harmonics and 11th harmonic, and then we can have all the harmonics currents here and harmonic voltage, and from which we can get the TAD in the voltage around 30% and current TAD will be order of 11.59% and interfacing inductance of 10 millihenry. Now, coming to ninth example, a 3-phase 12 pulse bidirectional boost converter, AC/DC converter, GTO based voltage source converter coupled to transformer, having a primary is connected to AC mains star delta and star with a common DC bus feeding 30 kilowatt from your DC battery of 760 volt to a 240 volt per phase 50 hertz 3-phase AC mains and sinusoidal wave shape. 11th harmonics current is to be limited 5% of the fundamental current. The displacement factor is corrected close to unity, and VSC is operated in the mode to cancel 5th and 7th harmonics in VSC output voltage. Determine A transformer turns ratio, B the fundamental phase current, C an output AC RMS voltage, D the phase shift in fundamental component of VSC voltage and the supply voltage, E 11th harmonic current, and D the TAD in VSC voltage and TAD of G as THD in AC current and H in value of AC inductor. Now, coming to numerical example, P equal to 30 kilowatt, supply voltage 240 volt 50 hertz per phase and DC link voltage 760 volt with power factor unity. So, we can find out turns ratio from given data. So, we get turns ratio 0.245 and fundamental phase current from this power relation. For unity power factor, we can get 41.6667 and AC output RMS voltage from converter voltage relation for typically for 3-phase. So, it comes 268.70 volt, and we can find out now 11th harmonics, which is 5% of fundamental. So, that comes 2.88 because we know fundamental current we calculated. So, from this we can get a even the reactance calculation, that comes 1.0669, and from this we can calculate the inductance. So, it comes 3.4 millihenry, and the phase shift from this relation, once we know the reactance and the typically the you can call it like a your supply voltage and converter fundamental, it comes 9.4, putting the value it comes 9.5 degree, and then we can have all dominant harmonic voltage, then dominating all harmonics current from this relation, and then we can have a TAD of the voltage, putting the relation here 14.17, which is just close to 15%, and the TAD in the current is 6.37 for given data, and the value of interfacing inductance which we calculated for to limit the your harmonics 11th harmonic less than 5%, it comes 3.4 millihenry. Now, coming to 10th example, a design a 3-phase 18 pulse power factor connected bidirectional boost converter GTO based voltage source coupled with the transformer primary connected in AC mains with bus following with the following specification: supply voltage per phase is 250 volt RMS and 50 hertz 3-phase supply. Output voltage is DC output is 240 volt, output power DC is 12 kilowatt with output voltage ripple less than 2%. 17th harmonic current is limited to 4% of the fundamental, and because it is 18 pulse, so you will not have less than 17th harmonic, and displacement factor is corrected to unity. The voltage source converter is operated to cancel 13th harmonics in VSC output to determine A transformer turns ratio, B fundamental phase current, C an output AC RMS voltage, D phase value of phase shift in fundamental component, and the E 17th harmonic current, F TAD in VSC AC voltage, and G TAD in AC phase current, and the H value of AC capacitor and AC inductor. So, coming to numerical part of it, we have given a data like frequency 50 hertz. So, we can find out typically omega 2 pi f. So, it is a 14 0.15 and voltage is 254. So, we can find out the output voltage is given 240 and power is given 12 kilowatt with power factor unity. So, we can find out the turns ratio from this relation. So, it comes 0.823 and fundamental phase current now we can find out from power and power factor relation. So, it comes 15.748 and the converter fundamental voltage from this relation of modulation index we get 84.8528 and value of phase shift now from power relation we can get delta equal to 4.96 degree. And then the harmonics which are there in 18 pulse less than 17 will not be there, lowest will be the 17, that will be V n upon n. So, V 1 by 17. So, we can have all dominant harmonics in voltage 4 dominant one and similarly for current it will be your n square x l. So, they will be like typically again 4 dominant harmonics of same order and we can find out the TAD in voltage taking the dominant harmonics. So, it comes 8.82. In 18 pulse we are supposed to get only order of this and the TAD in current is again 5.28%. So, that is also meets some time standard. And coming to AC capacitor and AC inductor. So, we say 17th harmonics is only 4% of fundamental. So, we get a 17th harmonic and we can get from this the now reactance value of 0. And from then we can find out corresponding to inductance value of 1.49 milli Henry and we have a now DC link you can say output current power divided by voltage. So, it comes 50 ampere. We can find out now fundamental current of the converter from typically this relation it comes 17.68 and we can find out the reactance virtually corresponding to this from this relation it comes 10.7287 ohm and the value of capacitor from this relation we get 296.69 microfarad and then we can have a typically 2% voltage ripple. So, from this second harmonic ripple we get 1660 microfarad and these are the typical references and followed by. Thank you very much.